My name is Arjit Shil. I am a third year undergraduate student of the Department of Mechanical Engineering enrolled in its BTech course. My roll number is 23ME10012. I am delighted to present this project alongside my teammates Siddharth Behra and Sadin Kumar Behra. We will be discussing a problem statement that involves designing and synthesize a simulator for a garage door mechanism that does not have any prismatic or higher kinematic pair and occupies less space to remain open. Let us check the overview of the approach. To address the problem, we structured our approach in three stages. First, we focused the understanding of Forer mechanism. This type of Forer linkage is fundamentally to our design as it involves revolute pairs, making it ideal for the given requirements. Second, synthesizing a Forer mechanism by overlay technique. This technique allows to design a linkage system that aligns with the problem's constraint and meets the requirement functionalities. Finally, we designing the garage door mechanism in the SolidWorks. This step was essential to ensure that the mechanism operates as it intended and fulfills the criteria outlined in the problem statement. Checking for Grashof condition. An important aspect of our analysis involved the checking for the Grashof condition. This condition determines whether a forward linkage can achieve continuous relative motion between its links. The sum of the shortest and the longest lengths, that is S plus L, is less than equal to the sum of the remaining two links, that is P plus Q. The mechanism is classified as the Grashof linkage, also known as the class 1 kinematic chain. In this case, at least one link is capable of making a full revolution with respect to the ground link. If the if the sum of the shortest and the longest link is greater than the remaining two links, that is P plus Q, then it is known as non-Grashof linkage. There is no link will be capable of a complete revolution relative to any other link in the mechanism. This is also called a class 2 kinematic chain. Now, my friend Siddharth will take over the synthesis.
My name is Siddharth Behra. My roll number is 23ME10082, and I am going to tell about synthesizing a 4R mechanism by fixing ground hinges O2 and O4 in three configuration and finding hinges A and B using overlay technique. We begin by identifying two fixed pivots O2 and O4 which remain constant throughout the motion. The garage door operates in three key configuration. First, we took the tracing paper in the second and third configuration, aligned them over the first configuration. By doing this, we are able to observe and mark the paths traced by O2 and O4 as the mechanism moved between the configurations. Next, to determine the exact location of the fixed pivots, we use the geometric property that the true center of the rotation lies at the intersection of the displacement lines. So for both O2 and O4, we construct perpendicular bisector for paths traced between the configuration, and their intersection points gave us the actual centers of rotation A and B. The first trial that we did, and we got this type of configuration. In this configuration, we get these measurements. By using these measurements, we used the CAD model.
This is our CAD model. Here you can see that the smallest link can rotate, uh, and so this tells us that it satisfies our Grashof criterion. But we cannot move this link in the first and second configuration, which means that we are somewhere wrong and we did our did our synthesis wrong. So we did another synthesis and we got our right results in the second trial. So let's go and see what we did in our second synthesis. This is our trial 2. We did our synthesis using the same procedure and got the desired synthesis and motion of links. And we got the measurement that we used to make the CAD model. So, so from here, Swadhin would be explaining about the CAD model and the motion of the CAD model.
Hello everyone, my name is Swadhin Kumar Behra. My roll number is 23ME10090. I will be explaining about the CAD model we have designed for this project. So here is the garage door mechanism we have designed in SolidWorks. And first of all, we have measured all the link dimensions from our synthesis we have done in our trials, mentioned in the earlier slides, and these links are also designed accordingly. Uh, Here you can see there is a base link, and this is another link. This is one link, and this is a link with its joints from this point to this point, and we have extended it to give a feel of door. And, and as you can see, if I try to move this door, we can move it from vertical to horizontal position. And we have also attached a gear here, which will allow allow gear here, and we can also attach a motor to it, which will allow us to move the garage door as we wish. And this, as the as you can see that the teeth of the gears in this link are at the end, which will give force at the end of this longest link, which will reduce the force required to lift the garage door. And and let's see, if we have applied the force to the shortest link, it will require a much force, right? As torque required is force into the perpendicular distance from the axis. And now another thing is we have added this topper, you can see that red one, which will stop the carriage door from moving any further backwards. And also there is a locking mechanism here. If I push this will stop this will keep it open. You can keep the garage door open at all time. And any kind of further improvements we can do is uh, moving from 4-bar linkage to a 6-bar linkage, which will smoothen the transitions. I think this is smooth too, but this requires a bit long links, which is not feasible for us. Right. And we can also add a hydraulic system, which will smoothen the smoothen the process a bit more, and it will also produce less noise than the motor gear we have used. And we can also add rubber bushings here in this face of the stopper so that it will land smoothly on this, and also on the base. So we can add that. So that's it from our side. Uh, Here I conclude this presentation, and thank you very much.